Welcome to Chapter 8, Sequences and Series. A sequence is an ordered collection of objects with a first member, second member, and so on. Sequences appear everywhere: population counts over time, bank deposits over years, and depreciating values. The famous Fibonacci sequence dates back to 1175. When sequences follow specific patterns, we call them progressions. What exactly is a sequence? It's an ordered list where each element has a position: first, second, third, and so on. We denote terms as A1, A2, A3, up to an, where the subscript indicates position. The nth term, called the general term, is the most important for finding patterns. Sequences can be finite or infinite. A finite sequence has a fixed number of terms, like counting ancestors over 300 years, which gives exactly 10 generations. An infinite sequence never ends, like the successive quotients when dividing 10 by 3, which continues forever. We can often find a formula for the nth term. For even numbers 2, 4, 6, 8, the nth term is an equals 2n. For odd numbers 1, 3, 5, 7, the nth term is an equals 2n minus 1. However, some sequences like the prime numbers 2, 3, 5, 7, 11 have no simple formula. The Fibonacci sequence is famous: 1, 1, 2, 5, 8, 13, 21, and so on. Each term is the sum of the two preceding terms. The recurrence relation is an equals an2 plus an1. This sequence appears throughout nature, in flower petals, pine cones, and shell spirals. A series is the sum of terms of a sequence. We write it as a1 plus a2 plus a3 and so on. The sigma notation uses the Greek letter sigma to indicate summation compactly, sum from k equals 1 to n of ak. Series can be finite or infinite, just like sequences. An arithmetic progression, or AP, is a sequence where each term differs from the previous by a constant. The form is a plus d, a plus 2d, a plus 3d, and so on. Here a is the first term and d is the common difference. For example, 3, 7, 11, 15, 19 has d equal to 4. The nth term of an AP is given by an equals a plus n minus 1 times d. The first term is a1 equals a. The last term, l equals a plus n minus 1 times d. For example, the 10th term of the sequence 2, 5, 8, 11 is 2 plus 9 times 3 equals 29. The sum of n terms of an AP has two formulas. Sn equals n over 2 times 2a plus n minus 1d. Alternatively, Sn equals n over 2 times a plus l, where l is the last term. For the sum of first n natural numbers, we get n times n plus 1 over 2. Sum of 1 to 10 equals 10 times 11 over 2 equals 55. The arithmetic mean between two numbers a and b is simply a plus b over 2. We can insert n arithmetic means between a and b, creating an arithmetic progression. The common difference becomes d equals b minus a over n plus 1. A geometric progression, or GP, is a sequence where each term is a constant multiple of the previous term. The form is ar squared, ar cubed, and so on. Here a is the first term and r is the common ratio. For example, 2, 6, 18, 54 has r equal to 3. The nth term of a GP is an equals a times r to the power n minus 1. The first term is a1 equals a. The last term, l equals a times r to the power n minus 1. For example, the fifth term of 3, 6, 12, 24 is 3 times 2 to the fourth power equals 48. The sum of n terms of a GP depends on r. If r equals 1, then Sn equals Na. If r is not 1, then Sn equals a times r to the n minus 1 over r minus 1. An alternative form is Sn equals a times 1 minus r to the n over 1 minus r. For 2, 4, 8, 16, the sum is 2 times 16 minus 1 over 2 minus 1 equals 30. The geometric mean between two positive numbers a and b is the square root of a times b. We can insert n geometric means between a and b, creating a geometric progression. The common ratio becomes r equals b over a to the power 1 over n plus 1. An important relationship. For any two positive numbers a and b, the arithmetic mean is always greater than or equal to the geometric mean. Equality holds only when a equals b. The difference am minus gm equals square root of a minus square root of b squared, all divided by 2. Special series formulas are worth memorizing. The sum of first n natural numbers is n times n plus 1 over 2. The sum of squares is n times n plus 1 times 2n plus 1 over 6. The sum of cubes is n times n plus 1 over 2 all squared. These appear frequently in problems. For infinite geometric series, when the absolute value of r is less than 1, the sum converges to a over 1 minus r. If the absolute value of r is greater than or equal to 1, the series diverges. For example, 1 plus 1/2 plus 1/4 plus equals 1 over 1 minus 1/2 equals 2. Real-life applications are everywhere. Compound interest uses geometric progressions. Population growth often follows geometric patterns. Radioactive decay decreases geometrically. Loan amortization schedules use arithmetic progressions for principal payments. Avoid common mistakes. Don't confuse AP with GP. Check whether terms have constant difference or constant ratio. Use the correct sum formula for each. For infinite series, always verify that the absolute value of r is less than 1. Watch for sign errors in the common difference. Key formulas to remember. For AP, the nth term is a plus n minus 1d, and the sum is n over 2 times 2a plus n minus 1d. For GP, the nth term is a times r to the n minus 1, and the sum is a times r to the n minus 1 over r minus 1. Problem-solving strategy. First, identify whether the sequence is an AP or GP by checking for constant difference or constant ratio. Find the first term and the common difference or ratio. Apply the appropriate formula. Determine if the sum is finite or infinite. Let's find the sum of 3, 7, 11, up to 20 terms. This is an AP with a equals 3, d equals 4, and n equals 20. Using the formula, S20 equals 20 over 2 times 3 plus 19 times 4. That's 10 times 6 plus 76 equals 10 times 82 equals 820. Which term of 2832 equals 131072? This is a GP with a equals 2 and r equals 4. We need n such that n equals 131072. So 2 times 4 to the n minus 1 equals 31072. Dividing by 2, 4 to the n minus 1 equals 65,536, which is 4 to the 8th. Therefore, n minus 1 equals 8, so n equals 9. An arithmetic geometric series has each term as a product of AP and GP terms. For example, 1 plus 2x plus 3x squared plus 4x cubed and so on. To sum such series, use a special technique. Multiply by the common ratio and subtract from the original series. In this chapter, we learned that sequences are ordered lists of numbers. An arithmetic progression has a constant difference between terms, while a geometric progression has a constant ratio. We derived important formulas for the nth term and sum of each type. These concepts have wide applications in finance, science, and nature. Thank you for joining Chapter 8 on sequences and series.